Diffusion, the international science radio show.
Yeah. So, hi, I'm Bonnie Teece, and I'm a PhD candidate at the Australian Centre for Astrobiology at UNSW.
Hi, my name is KIrsten Banks. I'm a PhD student at the University of New South Wales studying galactic archaeology.
And I'm Martin van Kranendonk. I'm the director of the Australian Centre for Astrobiology and a professor at the University of New South Wales.
Fantastic. Now, the Perseverance rover was launched just last week, and they're looking for life on Mars, and they spoke to the Astrobiology Centre, is that right?
We've been in touch and involved with the Mars 2020 Perseverance program for about the last 3 or 4 years. And last year we had the entire team on the Mars 2020 rover mission come to Australia, to the northwest of the country for a field trip. And it was a workshop where they, and for some of them, many for the first time, could have a look at ancient life on Earth in rocks about 3.5 billion years old that are about the same age as the rocks that they're traveling to Mars to look for signs of life. So for many of them, it was the first time to get a real appreciation of what these signatures of life looked like in the field. And also think about the challenges of, even just the really practical components, not even just trying to figure out what kind of wriggly texture and crack was important or not important, but actually how would we drill and where would we sample for this specific texture and what's the best criteria. And so really for a week, we just pored over these really important outcrops, and everybody sort of saw it with their own eyes and tried to apply their science and their instruments on Mars to what they were looking at under their feet. So yeah, it was a really rewarding trip for everyone, and Bonnie was involved in that, and we had a big team up there. It was great fun.
And the Pilbara sort of looks a little bit like Mars with all the red rocks and dirt.
It does indeed. It has a lot of components that are similar to Mars. Not so much the Mars we see today, and you're right, there's that look that everybody sort of equates between the two areas, but that's relatively superficial. On a much deeper level, the rocks up in the Pilbara are quite unique in the world because they're incredibly well preserved, but unbelievably old. 3.5 billion years is just a mind-boggling stretch of time. And it's about the same time that Mars was actually quite similar to Earth. It had rainfall, flowing rivers, it had volcanoes, and it had many of the ingredients of life that we know were important for starting life on Earth. And that's really Mars an exciting target because it has those kind of ingredients and maybe the Goldilocks environment of being not too far from the sun, not too close, but just having the right kind of ingredients that maybe life could have got started there. And so we're all about trying to understand, if you've got a whole planet to go and look, where would you go? What specific type of rock or environment would yield the best chance of success for finding perhaps extremely faint traces of life? We're not looking for dinosaurs here. We're looking for communities of microorganisms that leave behind tiny little signatures in the rock record that really need a specialist eye to eke out from the rocks. And that's part of what our training workshop up at the Pilbara was all about last year.
Would you like to add anything, Bonnie or Kirsten?
Yeah, one thing that I thought was really striking that I hadn't considered in great detail before that field trip was how we're really looking for very small pockets, like these rocks that could be the areas of best preservation. If you take the rover and you turn right and you miss those fossils, well, then you miss them. So understanding the context of the rocks, understanding where that life is most likely to be is really, really important to actually looking for that life.
And the whole process is pretty fraught. I mean, they've sent, was it a long time ago, in one of the very earliest rovers, they sent something to detect life, but it wasn't enough evidence.
So there have been a few detections which have made people question whether it could be a signal of life. Just a few years ago, the Curiosity rover detected some organic compounds, which started a conversation about whether these compounds were produced by biology or not. And it's most likely that they were not produced by biology, but were actually generated from a meteorite impact. So one of the key things when you're looking for life on other planets or in deep time is that you'd like to see multiple lines of evidence. You'd want to find chemical evidence, but also physical evidence and evidence in a lot of different ways to strengthen your argument that you found alien life.
That's a really good point, because we've kind of been burned before. You know, there was that huge expose in, I guess, the mid-90s about, you know, finding life on a Martian that came to Earth. And they had a couple of lines of evidence that looked really strong, but really when you know, people then analyzed it in great detail over decades, and they found that those, you know, lines of evidence have actually fell away as we learned more about it. And science is all about continual learning. We get better at what we do, and we find new techniques and develop technologies that can assist in our understanding. But Bonnie's point is really, really appropriate, because, you know, you and I, we're chemical systems, but we're also alive systems. And one of the huge challenges in looking at signs of life 3.5 billion years ago is how can you discriminate between life and just chemistry? Because everything will leave a chemical system, but how can you definitively prove that it was only made by life and not by a meteorite strike or groundwater or some other kind of chemical reaction? And that's really, you know, the forefront of our science, is learning how to discriminate between those different possibilities. And so, you know, that aspect of sending the rovers up, you're right. The Viking mission back in the 70s found some chemical traces that are associated with life, but nothing definitive. And so, for example, you know, now they're also finding these traces of methane on Mars. And methane is a gas that can be produced by life. So when cows belch, they produce methane. When, you know, so that's a signature of life. Well, you can also get methane through processes that don't involve life. So there's been lots of excitement and teasers, but nothing that is definitive yet. And now the bar for defining life, and especially ancient life, is unbelievably high. And it's really down to a few compounds that are specific to life, if you can find the organic molecules, or if you have something that's absolutely definitive in terms of a rock texture or something. But those are always controversial. So we're always trying to prod and find new ways to investigate. And so one of the key things about this Perseverance mission is collecting samples to bring back to Earth. Because even though we have an unbelievably sophisticated array of scientific tools launching to Mars on their way now that can probe and zing, and we got a laser, and we got elemental analyses, we got all sorts of things. But to prove life, those samples would have to come back to Earth, where we can apply the most sophisticated tests that use enormous instruments for analysis. And so that's really the next step in this interplanetary exploration, is to return samples back to Earth.
So I guess it just goes to show that finding life and being very sure about yourself is a very complex question to answer, and a very complex process of science as well. I'm not an astrobiologist, but I'm just enthralled by how much there needs to be done just to confirm or deny, or be somewhere in the middle, which is okay, which is, like Martin said, that's what science is. We're continuously improving upon our way to research and improving on our way to get to these definitive or close to definitive results. And I'm really excited for what the new Mars rover Perseverance will possibly get for us.
And so what sort of sensors does it have?
So Perseverance has a payload of instruments, and some of them are dedicated to helping find evidence of past life or characterizing geology. And some others are for things like preparing for future human exploration. Some of the key instruments that would be really integral in establishing life would be something like Pixel, which was designed by an Australian scientist and her team. And Pixel is an elemental mapper, and it can map elements at a really, really fine scale and really understand the interactions between different elements. And it can show if there was signs of life, those interactions between certain elements. There's also an instrument called Sherlock, which is a UV Raman spectrometer, which is a lot of words. And it is just something that can help pick up organic molecules on fine scale and give an idea about where those organics might lie. And so with different instruments, they have complementary information that you can use together to start building up that strong picture of evidence that we've just been talking about.
And another instrument that I really like on top of that is not just the instruments that are finding extra life, but there's also an instrument called MOXIE, which I really loved reading about when I first started reading about Percy. And it's the Mars Oxygen In Situ Resource Utilization Experiment. Again, lots of words. And MOXIE essentially is making oxygen from the Martian atmosphere, which I thought when I first read about it, oh, oxygen for future astronauts to breathe when they go to Mars. But it's not just that. It's also to create liquid oxygen to provide fuel to potentially launch back off of the red planet when we're ready to come back home. And also, not to mention, there are 23 cameras on Percy, so plenty of opportunity for selfies.
But by far the best instrument, I think, or the most exciting instrument is the Supercam. That's one of the 23 cameras that Kirsten just mentioned, but it's a total sci-fi experiment. It sits right on the masthead, so looking forward, and it's a camera and a laser and an elemental analyzer at the same time. This thing is the best thing ever. I wish I had one in the field with me, but it can zap a laser about the size of the point of a pencil on a rock up to 7 meters away. And then it vaporizes a bit of the rock. And as that vapor is in the cloud, it has a spectrometer that can sense what the minerals are. And so it actually does this, far away analysis of rocks. And so it can just go up there and go zap, 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 zap. Oh, we'll take that one, not that one. And it's just the best thing.
That's so cool. I can just imagine Percy being like, pew, pew, find minerals. Let's go.
That's exactly what it's doing. And then all the other sophisticated machines that Bonnie and Kirsten talked about are really as follow-up. And as a geologist, that's really very much how we go about our science as well. We use our eyes in the first instance to go up to a rock and say, oh, that looks interesting. Then we get our hammer, we collect the sample, and we take it back to our laboratories where we do the laser analysis and the elemental spectrometry and all the rest of it. But the Perseverance rover has that capacity built in a vehicle about the size of an SUV or so, and it can just wheel around and do its analyses on the go. I wish I had one of those for my field work. It would be amazing.
A bit of drive-by geology.
Drive-by geology for a mere $2 billion.
There was something online about it collecting samples of soil as well, and I didn't know what it was going to do with them once it sort of put them in little jars or something on the rover. Did I get the wrong idea?
They're going to just drop them.
Yeah, so the idea with the current rover that's up there with Curiosity, they can drill and take samples of soil or of rock, and they can analyze it in the machine itself, in the rover itself. And they get a whole bunch of information about that. But in this case, what they decided to do was have a suite of instruments that would be able to identify the most exciting type of sample material on the ground, and then collect them, either the soil or the rock or the dirt, and put it in those little tubes and bring those back to Earth. So they won't do a lot of analysis on Mars, but they'll identify the best, most likely samples to collect. And they've decided on a whole suite of samples. So some will specifically look for life, and others will inform us about how Mars formed and evolved as a planet. And so that collection of samples, I think it's 21 or 27 or something like that, will then be put in a storage place all together and basically just left on the surface of Mars until they can send a second mission to come and pick those samples up, blast them back into orbit around Mars, and then in fact a third mission will have to come and pick up those samples from orbit and bring them back to our labs. And it just shows, you know, that Mars is so far away and the technology is right at the limit of what we're capable of. In fact, mission 2 and mission 3 aren't even fully designed yet. So they're planning well ahead of where the technology is, kind of forecasting where we'll be in a decade's time to bring those samples back. So wait a while, it won't be until the very earliest 2031 before those samples can come back, and maybe later than then. But it's a great challenge. And the interesting thing is that's really inspired a new race in, well, it's not really a race, but there's a new rush of investigations for Mars. So, you know, it's not just NASA that's launched, but the United Arab Emirates have launched a satellite. China has launched a rover that will land on Mars. And the European Space Agency, who were supposed to launch this year also, they've been delayed for a couple of years, but they're launching a rover themselves in a couple of years. So there's actually a lot of activity, and it sort of seems like Mars is the forefront that allows us to challenge ourselves and see what we can do. So it's a really exciting time to be involved.
So get out there, kids. You can get a job in Martian exploration.
There you go. And it is incredibly difficult thing that they're doing, isn't it? It's just amazing the enormous distance and the time and the control and the automation and just getting everything right. And of course, even just and then landing the rover on Mars itself doesn't always work.
That's right. Landing on Mars is very, very difficult. Trying to get through the atmosphere and land safely. It's called the 7 minutes of hell, dubbed by NASA, because by the time that Percy gets to Mars, it will be in around mid-February. And when in mid-February, Mars will be at least 9 light minutes away from the Earth. So any sort of signal we get from Percy will be a 9-minute delay. So by the time we get that signal saying, hi, I'm at the top of the atmosphere right now, I'm making my way down, Percy would have already landed, either safely or crash landed, and hopefully safely.
And at that distance, remote control, there's no hope at all over 9 minutes.
No hope at all. It's just sit back, cross everything, and hope. Hope that your science and your engineering has been enough to land safely on Mars, which at this point should be very good because we've landed, well, we as in NASA and many other organizations have landed many successful missions on Mars. So should be all good. But again, fingers crossed. Never know what can happen.
So the Centre for Astrobiology, in addition to the Mars mission, what else have you been engaged in?
Well, Bonnie and I and another couple of PhD students have attended by invitation the NASA workshops to choose a landing site. So I mentioned before that, you know, if you've got an entire planet to go and explore, where would you actually go? You know, would you look, you know, informally if there was a deep ocean, or would you go look in lakes or rivers or a cave or the land surface? You know, what kinds of rocks, sandstone, conglomerate, limestone? You know, you've got this endless choice of material to investigate, but what is the single place? If you can get to one spot on Earth, like for example, where would you go? Most people would choose a beautiful tropical reef, of course. Those probably never existed on Mars. So the question is, how do you find that needle in a haystack? And so for really 5 or 6 years, the community as a whole by invitation from NASA, was brought together to discuss what would be the best sites to land in. And there are about 30 or so sites originally. They got whittled down to 8, and then eventually to 3, and finally down to the chosen site. So they're going to this location called Jezero Crater, which is one of a million billion craters on Mars. But this one specifically has a beautiful river that was flowing into it about 3 billion years ago. And when that river came over the lip of the crater and fell into the bottom, it let its sediment load out into a beautiful delta. So think the Mississippi Delta, or the deltas that are out in front of any of the big rivers. Those on Earth are rich in organic matter. In fact, some of our biggest petroleum finds or hydrocarbon reserves are from those kinds of deposits. And so they identified that as a potential place to look for a signature of Mars, of life. And specifically, they found that in the Jezero Delta, there were clays at the very far end of the delta, what they call the toe of the delta. And clays are known to be able to bind to organic matter. And so they figure that clays can actually, absorb and concentrate organic matter that may have been washed in by the river, or they're very fertile places on their own with nutrients that could have had its own microbial population. So that's the prime mission target, are those clays at the toe of the Jezero Delta. And then there are a whole bunch of other rock types that they can look at. But it was interesting being part of that discussion, because there was everything from like a deep valley deposit to go and look at caves, to look at hot spring deposits, which is the place that we were advocating for. But in the end, the community actually all voted. The first time I went there, they actually had, from all these different landing sites, then they actually had, the whole room of, NASA scientists and engineers and academics and postgrad students and grad students. They actually had them just sit there and put their hand up and say, I vote for this. And so it came to sort of a green light, orange light, red light kind of voting scenario. And yeah, that's how the sites were actually whittled down. And in the end, then those 3 sites were recommended to the expert panel, and they chose to go to Jezero. But our site with the hot spring deposits was in the top 3. So we were involved right until the very end decision. And we still think that's a very good site to go to, a very exciting place to go and investigate. But Jezero also will have lots of exciting information for sure.
If we try to go further afield than Mars, are there other ways we can look at faint signs of non-chemical reactions of something that might be life further than Mars?
So with exoplanets, the main struggle with trying to find any sort of signs of life on an exoplanet is distance. They're a lot farther away than Mars, than Venus, than Mercury, any of the planets or potential moons within our solar system that might potentially harvest life. And we also have to deal with the brightness of the star that these planets orbit around as well. So not only is it difficult to detect any sort of life signatures on an exoplanet, it's also difficult to detect exoplanets full stop, depending on what sort of configuration they're in, whether we are detecting them by the transit method. So if a planet passes in front of its star, momentarily dipping the light of its star, or dimming rather, or if it's in other forms as well. There have been some signatures that we have seen in exoplanet studies where they have been able to understand the atmosphere around a particular exoplanet, which is very, very cool. But as far as I know, that's about the top tier of detail that we can get from exoplanets at this current time with our technology.
Well, we're also able to explore some other very distant worlds. And, some of those include moons of the giant gas planets in our outer solar system. And so I know there are 2 really exciting missions that are going ahead. One is to Enceladus, which is a large moon of Saturn that's covered by water ice, by ice. And through that ice, through cracks in that ice, there are these jets of water that are coming out into space. And we've been involved actually with a colleague of ours from the University of Santa Cruz in California, Dave Deemer, who's designed this technology that can analyze tiny amounts of organic matter in a patented technology called nanopore. And the idea is to actually fly through those water jets with his little organic molecule detector, nanopore, on the mission. And that can actually isolate if there's strands of RNA or DNA, you know, the building blocks of life. So they can look for these complex life signature molecules, not by even landing on the planet, but just by flying through its spit, basically. I love it. And the other big one is they're planning a mission to the moon Titan. And Titan's really interesting because it has lakes of liquid methane. You know, it's a totally alien world, but it's, again, rich in organic molecules, perhaps, you know, the right elements for building up life. And they're planning to send a helicopter to Titan and go and sample the lakes. So there's lots of exciting exploration of our own solar system. And then the exoplanets, they're harder and harder. Each of those is like a step of magnitude of order more difficulty. But with exoplanets, one thing they can do is now they've refined their technology, they can start to look at the atmosphere of the planets. And so some planets have, you know, just carbon dioxide, some have nitrogen like us, and others have oxygen. As far as we know, Earth is unique in having a lot of oxygen, and that's actually a biosignature. The oxygen is produced by life in enough of a concentration to maintain that 17% global, you know, oxygen content. And so people have started to think about, can we just analyze the spectra of planets? And if they diverge from what's expected, maybe that's something to explore more fully and could be even a biosignature, what they call a signature of life. As a nation, we should be very proud that there are 3 Australians who have been and who are intimately involved with the Mars 2020 mission. 2 are the principal scientist and deputy scientist for the Pixel instrument on Perseverance rover. They're actually the ones who are leading, who designed, who nominated that instrument to go on board, and will be running the science when the rover lands on the surface. And then we have another Australian, Adrian Brown, who's at NASA headquarters, who's the deputy project scientist for Mars 2020. He's been helping to organize and do all the administration and logistics to get that mission going. And all 3 of those Australians were trained at the Australian Centre of Astrobiology. And so we're very proud that we have a long-standing and continuing relationship with space exploration that involves Australians at the very highest level of international science. And I think that's something that the whole country can be justifiably proud of.
Absolutely. You know, in Australia, we're really fortunate to hold these rocks that we've been talking about earlier that are such good preservers of such ancient life. And these rocks become the training ground for the next generations of astrobiologists and for thinking about what Mars could have looked like. So in Australia, we're producing world-class astrobiologists that can work at the highest level that have been trained on rocks from our country. And it's a significant contribution for our country to be making.
Absolutely, and I think Kirsten really, you know, touched on that as well. Is that you may think that, you know, Australia is far away and these projects are big and very remote, but it's not. You know, if you've got a passion for science and for getting involved in any sort of endeavor, there are always opportunities. And the world, maybe not right now in COVID-19, but the world is a relatively small place and interchangeable. You know, the science community is one where people know one another. Even though there are researchers all around the world, the specific fields become like a family. And it's a really nurturing environment for becoming involved. And so, you know, I was talking about going to the landing site workshops. You know, that was one of the great opportunities to be able to bring students along and get exposed to what's going on and get involved and make connections and stuff. So it's that kind of a world that science fosters. And Kirsten would know that. She's been involved in a lot of opportunities, gets invited to lots of different kind of events, and then asked to lead events. And that's a natural progression. And you know, depending on your passion, involvement, skill, and talents, you can move right up and be involved in unbelievable, exciting research of new discoveries. And so that's a real opportunity that science provides and that Australia has and does very well.
I totally agree.
Well, if there's nothing else, Bonnie, Kirsten, Martin, thank you very much.
Thank you
Thank
so
you, this
much
has
for
been
having
fun.
us, Ian.
Our pleasure, Ian.